Sure. Absolutely, go for it. Have a good day.
So I just finished putting all the variables in the observation list. And I basically have 4 blue stars, 2 red supergiants, and 4 unclassifieds. Does that sound good, Rafael?
Sure, yeah. Don't have any problems with that. I imagine you probably thought a bit about which stars to choose and if we're increasing the cadence of any of our old observations.
And also, like Monika just said, to prioritize those, so I just decided to do exactly that.
Yeah, no, that's perfect.
Oh, another thing I wanted to mention is that the target list is in the chords GUI on the screen, Kevin. So you can just pick from there for the variables.
Yes. Yeah. Thanks.
So I've placed the red box around what I believe to be your target. Can you please confirm?
Gotta rotate my head a bit. Looking for a bright star to the east and south. What's the scale? What's the scale of the guider again?
It's about 60 arc seconds across.
Okay. So I'm looking at approximately the same image over here.
So 10 arc seconds away, there's something that's to the east-southeast, right?
Yeah, and something that's to the, there should be another bright object.
Very bright star to the east.
To almost south, I'd say south by southwest.
That one? That one, okay. Can you see the really bright thing in your finding chart? The one that's due east of the target? The really bright
Zoom
one.
Out just a little bit more to make sure. Sorry, did you say 60 arc seconds?
It's actually about 90 arc seconds across in mirror position 2.
Okay. So about 45 arc seconds due directly. Okay, yeah. I'm starting to get oriented a little bit. Yes, yeah, I completely agree. You're on the target.
Okay, I'll get that on the slip.
Okay.
And once we start a long exposure, we'll go around and explain what we're doing, of course.
Yes, yeah, we'll be here for about 1200 seconds.
20 minutes.
Okay, you take the slip back. Center.
Split is back.
And we are guiding. You may begin.
Okay, there we go.
Yeah, you know where it is?
Okay, perfect. Rajo, were there more introductions you wanted to do, or do you want to walk through the screens here?
There's a couple more very quick introductions, okay, Kevin, that just a few more people that I'd like to put on the spot. I think Flora is a SIP intern this year. Flora, did you want to say a quick word? If you feel free to say no, of course.
Yeah, I'm a SIP intern this year, but I'm really enjoying this and also getting the opportunity to watch you guys do research as well.
Flora, what subject area are you working in astronomy?
Astro 3, so we're looking at scaling relations with galaxy clusters.
I see. Yeah, this is with Tesla and her group.
Yeah.
Excellent. Let's see, who else do I recognize? Bree, how are you?
Hi, Raja. So good.
So I thought of you earlier today, Bree, because so Bree, you work in the Office of Research, right, at UCSC?
Right. Exactly.
Someone brought up, someone in Cosmos today asked me, do I know any SIP interns who speak Russian?
Amazing.
That made me think of you and made me think of Andrew specifically.
I love it. I'll have to tell him. That's
Okay,
awesome.
I might put him in touch with this student who reached out.
Yeah, definitely do.
We have students from Russia this summer, but we have other Russian speaking students who are not from Russia also. But I'll put her in touch with Andrew.
Perfect.
Thank you for staying up late to
Oh my
watch
gosh,
the
no,
fun.
this is so exciting. This is awesome. It's so cool to see this in action.
And Anand, did you want to say a quick word? Thanks, Brit. Thank you.
Yes, I can turn my camera on too this late at night, but I'm excited to be here, kicking off the STS events. I'm part of the science internship program. I work with Raja. I'm the operations coordinator. We've had our 2022 cohort going strong. We've got 1 week left, and yeah, I'm excited to be here.
Thanks, Anand. I don't recognize everybody's Zoom name. I do recognize Mark Chen. Give a moment. Mark says hello. Mark is one of our program assistants, also helping with the SIP program. We've invited a bunch of SIP students, all the ones working on astro research, to today's session. Lila, did you want to welcome? Thank you for being part of this. Lila, if you have a moment to introduce yourself, we'd love that. But if you, it's late at night where you are. It's past midnight, so I completely understand. Hi. So Lila is a high school student in all the way on the East Coast who's interested in astronomy, and we invited her to take part in today's session. We'll be doing another session a little bit later tonight from 1 to 3 Pacific, and then we have 2 more sessions in August. Emily, at this rate, it looks like we may be able to do as many as 50 sessions before the end of the calendar year, which is way more than I had anticipated, or we had anticipated in the proposal.
Yeah, that's fantastic.
I know, we had talked about working up to 1 a week in year 3, but if we get 50 done between now and December, we'll be well ahead of that curve, but we'll see. So I'm gonna hand it over to Stephanie, Rafael, Kevin, if you want to talk about what the different screens are. I know there have been some questions in the chat about what we're seeing. So please.
Well, I guess I can explain things as I'm doing it. So as I've been flicking through my screens here, one of the things I'm doing is looking at the targets that Stephanie, Rafael, and Stefan have put together, and just queuing up what we're doing next, because time on telescopes is difficult to get and expensive. So you want to be as efficient as possible when you have your time. So I try to load everything up so that we don't have, or we have as few downtime moments as possible. But luckily it's not super stressful because generally the things we're looking at are quite faint. And so we have 10 plus minutes usually on each target for me to get the next one ready. Okay, so basically what we're looking at here is kind of a reproduction of the different screens that the folks on the mountain are looking at. And there's kind of 3 main screens that we'll focus on. This is the first one, this is the second one, and this is the third one. The first one is what I usually call the blue screen. It's where the information for the blue detector of our instrument is. And then the second screen is our red screen, which is where the red information is. And then the final screen is the guiding screen. So basically, as the light enters the telescope, we are blocking out everything except for the light of the star that we're interested in. And then that light gets split up into a rainbow, past kind of like through a prism. The white light of the star gets split up into a rainbow, and then we break that light in half so that the red half of the light goes down one side of the detector, one side of the instrument, and then the blue light goes down the other side of the instrument. And so that's what I mean when I say a red side and a blue side. In terms of actual wavelengths that we're looking at here, we're basically covering the full range of wavelengths that your eye sees. We're going from slightly bluer than your eye can see, so into the slight ultraviolet, all the way to slightly redder than your eye can see. And then where the two detectors split the light is at around kind of what your eye would register as green. And so on each of these panels, here what we're seeing is the actual information that we're collecting. So this is the CCD has read out, and you see a few things, but the main thing that we're interested in is this streak of light here. This is the light from the star being bent out into the rainbow. And the left side of this image is the bluest wavelengths, and then it increases towards greener colors at this edge. And then when we cover the second screen, it picks right off where the other one left off at the top. So this is green colors on the top here. And then as we move down the detector, we're moving towards redder and redder wavelengths until we get to slightly redder than your eye can see. And so this line that we're seeing on this one detector is the star's light, and then it picks up now in the vertical direction here. Also, please, someone jump in if it says my internet's unstable. So if I'm cutting in and out, please let me know.
Kevin, you're fine. We can,
good.
at least I can hear you fine. And so what you're saying is, even though you're calling this the colors of the rainbow, we can't see the colors, but there's a mapping. There's a one-to-one mapping from X position to wavelength or color for this, for the blue half of the spectrograph. We are using what's called a double spectrograph. And there's a mapping from wavelength, from Y coordinate to wavelength for the way this spectrum, for the way the red side spectrum is displayed here. So the one-to-one mapping. And so if we could, if you could show the wavelengths associated with each pixel, you'd see it get go from, as Kevin said, green at the for this one, it would be green on the far right, and the sort of the BIV of Roy G. BIV would be on the to the left of the, would be in the main part of the spectrum. So there'd be violet, or even, as Kevin said, more ultraviolet, more into the ultraviolet than violet in the sort of middle of the screen. Then there'd be blue. Then there'd be there'd be indigo in between, violet, indigo, blue, and then green would be at the far right end of this. And in the other spectrum, the red half spectrum, it would be green at the top, and then it would yellow, orange, red, and infrared working downwards. So, one of my faculty colleagues used to say a spectrum is worth 1,000 pictures. A spectrum really has a lot of physics in it, and specifically through the branch of physics that's called quantum mechanics, one can take the spectrum of an object and learn a lot about what's going on inside the object, what's temperature, pressure, of a star. These are the chemical composition. These are things one can learn by taking a spectrum. That's what we're trying to do.
Yeah, let me see if I can pull up. The last star was significantly brighter, so we'll go back to that.
Yeah, and also one of the displays you showed, Kevin, showed in the night sky hasn't completely darkened, so you could see the slit there. I was hoping.
Yes.
Quickly flashed at that one. I
Yes.
think it's 2 over. Yeah. One more over. I think the one with the guider.
Oh, you wanted to see the big guider.
Yeah.
Sure. View.
Yeah, you can sort of make this out here, right? If you look closely at this purple rectangle, oh, there we go. You could see that there's a dark horizontal line through it, what's happening is that's the slit Kevin was talking about. We want to isolate the light of a star. What we do is we take a metal plate and cut a narrow rectangle into it, and we position the telescope so the star we're interested in, its focus light goes through that slit, whereas the rest of the metal reflects light and produces this image. So the star we're actually interested, we're not seeing. That's where Kevin's cursor is pointed. There's a little finger pointing to that also right above that. That's the finger. There's all kinds, you see all kinds of other patterns. This is called the guider. This is a small camera that is on the peripheral to the main camera of the telescope that lets us make sure we're pointed at the right part of sky.
Yeah, and it can also lock on to one of these nearby bright stars, and it's constantly checking to make sure that it hasn't moved with respect to the telescope, or if it needs to adjust the telescope so that the thing that we're interested in hasn't moved outside of the slit.
Right,
so each one of these bright spots are nearby stars and galaxies.
So we have to compensate for the Earth's rotation, nothing else. And that's why we use stars to fine-tune that compensation. So the telescope is rotating at equal, if you like, swinging equal and opposite to the Earth's rotation, so to keep a star fixed in its sights.
Exactly. And so this is the name. We are, okay, everything's going well. So for, like Raja said, I've gone back to our last star because it was a little bit brighter and we can point out some things. But if I draw a line along the star's light here and ask how much light is in each one of those pixels as a function of pixel or as a function of wavelength, because remember, these are wavelengths. Basically what we get is this, this figure right here, this graph, which is saying that as you're at the very lowest, the bluest wavelengths, there's hardly any starlight, but as you move towards these wavelengths, so these are more moderate blue colors that your eye could see, the star has a substantial amount of light. And so this shape here is caused by the physics of the star. It has to do with like how dense it is, mainly the temperature. And so those are some of the properties that we can learn by collecting the star's spectrum. Oh, that did.
Yeah, this is, Kevin, a great point here about the shape of the spectrum. There's three factors at play, right? One is, what is the star's temperature and how much light is it actually putting out? The second factor at play is, what is the Earth's atmosphere doing in terms of absorbing? Because the Earth's atmosphere does absorb ultraviolet light beyond some wavelength. And then even if the Earth's atmosphere went there and the star were putting out lots of light, the silicon device we're using, the camera, the glasses we're using, they become less and less efficient at reflecting light at very short wavelengths. So we're seeing a combined effect of instrumental response, atmospheric absorption, and of course the star's properties itself.
Exactly. And so one of the other things that we're interested in, like Raja said, was getting a handle or a sense of the chemical properties of these stars. And what you'll notice is that there are occasionally these strong dips and bumps along the spectrum here. So we can zoom in on one of them, something like this. And once we've done some of the post-processing that some of my colleagues had talked about, something like what Stephanie has been leading in our group, we're able to figure out what pixels correspond to which wavelengths. But even just by eye, we can zoom in on particular regions, and based on the shapes of some of these features, we know what wavelengths they occur at. And more importantly, I know what chemical element produces this particular feature with this particular shape. In this case, what we're looking at is a feature that's caused by magnesium in the atmosphere of the star. So the starlight is leaving the center of the star, and then as it passes through the outer layers of the star, it interacts with the chemicals in the outer layers of that star, and the kind of the chemical fingerprints of that outer layer of the star get imprinted on the light that comes towards us. And so this dip in the light here is because of magnesium. And so one of the things that we can do is we can come in and we can measure the strength of this feature to learn things about the amount of magnesium in the atmosphere of the star. And so that's, you know, some of the other information that we can collect from a spectrum. So yeah, we can play the same game with different chemicals and different features and use that to quantify the amounts of different elements in the atmospheres of these stars. And then we can use that information to figure out kind of the conditions that the star was born in. So there's a lot of really cool information that we're collecting here.
There's some excellent questions in the chat that I'm going to answer in the chat.
Okay. I can answer one of them. What objects are we studying right now? Great question. I should have said this earlier. Oh gosh, why does this keep happening?
I'm going to put the name of the project in the chat.
Yes. Okay, so the objects that we're studying right now are so-called transients. These are stars, or these are objects in the sky. I don't think it ended. I think we still got one more exposure. 1 second. Yes. Still one more exposure. Good. Okay. So the objects that we're studying right now are called transients. And so they're anything that wasn't in the sky when you were looking there earlier, that tends not to repeat. So there's if you take a picture of the night sky in a patch, and then you take another picture in that same patch of sky, for the most part, that won't change on a night-to-night basis. So you can take the two images and you can subtract them, and generally you'll be left over with no information. But some things, if you play this game of subtracting two images, some things will appear to brighten or dim over time. And so those are some of the objects that we're interested in this project. The main two types of stars that change over time that we're interested in are transients and variable stars. Variable stars tend to kind of oscillate in terms of their brightness over time. They'll get fainter, they'll get brighter, they'll get fainter, they'll get brighter. But generally they're visible in all of their states. And they tend to repeat oftentimes. Whereas transients are generally something that you didn't see anything there before, and now suddenly there's something quite clearly there. And oftentimes, if it's something like a supernova, given enough time, it will disappear completely, and we will never be able to see it again, just because the amount of light it's emitting is decreasing over time. And so the objects that we're focusing on at the beginning of tonight's observations, like the things we're looking at right now, are the transient class of stars. And so I can look at the exact one that we're looking at. Let's see if I have any information on this. Go to someone else's webpage. Raja, if you're muted right now.
Sorry, I was going to say this very clever acronym, thank you, is the project, is the name of the project we're doing tonight. And it's called Salvation because it's spectroscopy of luminous variable stars and also transients. And in our neighbor refers to the Andromeda galaxy. It's our neighboring galaxy.
So one of my backup screens that I'll move it over so you can't see it, is this information here. So I have a list of targets that we're interested in, but one of this is the patch of sky that we're looking at right now. This is a historical image, so it looks like there's nothing in this patch of sky that we're looking at right where we're interested, because it's a transient object. There didn't seem to be anything there before. And this here is its light curve. So this is just measuring how bright it is over time. So the x-axis here is time. And you can see that it's pretty much nothing, 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 nothing. And then suddenly it's starting, whatever is in this patch of sky brightened and is starting to decrease. And so you can see some of these different I talked about, where these are multiple observations of the same patch of sky that have been subtracted from each other. And now it looks like there's something there where there previously wasn't. And based on the information here, it seems like it's probably a type supernova. which just means that the type of star that it is, or the type of explosion that is. A type 1a supernova is actually a pretty kind of fun one. It's where a lot of the this type of explosion is where iron in the universe is produced from. So almost all of the iron that you're familiar with came from an event like this one. And the mechanism is generally you have a star that went through, or not so much like our sun. Anyway, it's a star that ended its life, and it has a neighboring star nearby. And the one star that's ended its life is very dense, and the star that hasn't died yet, as it reaches the end of its life, it will start transferring mass onto the surface of the other star. And at a certain point, the amount of mass that it's transferred exceeds a limit, and it causes the big supernova explosion that we're seeing here, and produces a lot of the iron in the universe. Yeah. Raja, is there anything you'd add to my explanation?
No, I think this is great. I think this is very good. I mean, we are, I was just going to add in the chat that, stars are very well studied and well understood entities, at least in a relative sense in astronomy. But, in the present era of astronomical research, one of the great topics of focus are things that change in the night, not things that change steady like our sun, but things that change, variable stars, transients. Kevin mentioned exploding stars. There are moving objects as well, where something appears in one place one night and somewhere else some other night. So this world of the changing universe is gaining more and more, this field of study of the changing universe is gaining more and more momentum. I know NOIRLab is in this game. The Rubin Observatory, which is going to be a game changer in this area. It's a telescope built that's in Chile that's getting ready to do a time domain survey of the universe like there's never been one before, not that level of detail. We're a small part of this enterprise to study things that are changing, not things that are static. And there's a lot to be learned from the changing universe that we haven't yet tapped into.
Exactly. Yeah, and one of the, and maybe some of my teammates could speak more about this, but one of the kind of the open questions we are working on with this particular project, with the transients, a lot of what we're doing is confirmation, because these things are only available to be seen by telescopes for a short period of time, and some events are rarer than others. A lot of what we're trying to do is just classify what types of events these are. And so getting a spectrum is a great way to do that, to decide whether it's one type of supernova event versus another. But when it comes to the variable stars, there have been kind of this growing list of different types of variable stars that weren't previously known. And so trying to understand the physics that produces all of these different types of variables is pretty important for, understanding the laws of the universe and understanding the different conditions that will produce different types of stars, and especially physics that we don't understand yet. And so some of the work we're doing is measuring these variable stars at different periods as they're changing their properties, as they're changing their brightness. And by measuring how their properties change with how their brightness is changing, we're hoping to learn more about the physics that governs these kind of strange stars.
Emily wished us good luck for the rest of the night. She had to log off, but and I sent a brief introduction for Stefan and Monika in the chat. This is a great time for anyone in the Zoom room to ask questions. I hope I haven't missed anyone I know in terms of putting you on the spot. You're probably feeling very happy that I've missed you and haven't put you on the spot. But if anyone wants to ask a question or have a comment about what you're seeing, please feel free. We are recording this session, and we will post the recording. Christy, welcome. If I can put you on the spot to say a few words about who you are, and I will also say that it's Christy was there very much on the ground floor when we started this idea of using pajama mode observing as an opportunity. So Christy, please, I know it's late, but if you want to say a word or two, please.
Hi, thanks, Raja. It's so great to be here and to see Shadow the Scientist in action. So thank you. I'm only going to be here for a few more minutes, but I definitely wanted to hop on.
You know what the previous incarnation of this project was called, Christy, so you're one of the few people who does.
We do. Raja, well, I'm blinking. Sorry.
I'm putting you on the spot.
You are putting me on the spot.
It's a Vincent van Gogh painting.
Oh, Starry, Starry Night.
This was our trick to keep the clouds away by calling the project Starry, Starry Night and not Cloudy, Cloudy Night. But yeah, and people would ask us, what does that even mean? And then they took matters into their own hands and started calling us Shadow the Astronomer. And we didn't like that because astronomy is a team sport, not it's astronomers. And then we also had this ambition of spreading this work to other scientists, not just astronomers. Many scientists
Raja, I'm breaking in because
Please,
we're reading out. I am sending new coordinates to POCO, and we are ready to move.
Okay, on the move.
Okay. And as we move the telescope, you'll see these streaks appearing in the guider camera. As the telescope is actually moving, the starlight is moving across the plane of the camera here, and so they appear as streaks. And I have a PA of, just 1 second. So this is a magnitude 19. It's in a host galaxy that's pretty small.
I'm sorry, what was the PA?
The PA is 188.
188, is that correct?
Yeah.
188.
Okay, so we've gotten close to this patch of sky that we want to be in, but now we want to rotate the telescope, which you just saw happen here potentially, so that we collect as much starlight as possible.
Okay, I believe your object to be at the center of that box.
So directly south of it, about 15 arc seconds away, there should be a relatively bright couple stars. Yep, and I see the, yeah, I believe you're correct.
That be your right object to the north.
Yeah.
Okay, I will get that on the slip.
Did I narrow the slit? Not yet. Okay. So now you can see the fine adjustments that Sean's doing to move our star into the here, this horizontal dark spot.
Kevin, is this the half arc second white slit?
Yeah.
Okay, so what we do here is we make the rectangle very narrow by, it's actually an adjustable slit, so we make it very narrow. And so when the star looks like a perfect hamburger where equal amounts are sticking out above and below, then we know it's perfectly centered on that narrow slit, and then we open up the slit jaw so that all of its light is going into the slit. This is sort of the method we use to line things up.
You may begin your exposure.
Okay, opening slit. And beginning. Okay, we will be here for another 30 minutes. Sorry, Raja, if you want to go back to your introductions.
No, this is good. This is good. Christy actually had to hop off. Christy was very much, Christy was working for SIP at that time and was in charge of fundraising for us. So for the first time we did something like this, it was for parents of from SIP alumni parents who were donated to the program. We did this sort of as a thing saying, would you be interested in seeing how this works? And they totally latched onto this. They said, you should just do this more widely and make this an educational opportunity. So that's Christy was very much in the on the ground floor.
Nice. Okay, and so for those who are curious, the object that we're looking at is inside of a host galaxy. Oftentimes the transients that we're looking at live inside of a host galaxy. Most stars do. But one of the fun facts is that as a star goes supernova, the single supernova briefly can outshine the entire rest of the galaxy. So the light from that one event can be brighter than the rest of the entire galaxy.
This is the question that Jim was asking, and it depends on how big and luminous the host galaxy is. Supernovae also come in different flavors. Type 1a supernovae are more luminous than type 2 supernovae. But a type 1a supernova, if it's a modest-sized galaxy, as Kevin says, can be outshone by a single exploding star. But if it's a very massive galaxy with lots and lots of stars, then a supernova doesn't outshine it. Single supernova doesn't.
So for those curious, it looks like the classifier is saying that this one has about an equal chance of being a supernova event or bogus. So I guess we will decide after the first exposure.
Are you using the LRC
Yeah, the LRC.
Yeah, sometimes they are vastly wrong when they say bogus though. So
okay.
That's been a fun discussion that I've had with Monika before, where you look at the alert, see what they think it is, and it's just like, it's definitely not bogus. So they're lost.
Gotcha.
And who called it bogus again? DLRC?
No,
LRC.
ALERCE.
ALRRC. What does that stand for?
That's a great question.
ALERCE.
Yeah, I think this is it.
ALERCE, is it?
Mm-hmm.
Yeah, it's one of the brokers. I think that's the one out of UK.
Yeah, it's like a competitor with Antares too, kind of. One of the things that we've been trying to work on is a similar classifier, but they got theirs out first.
But it's coming from ZTF, I think, the original observations. Is it a broker that's filtering ZTF data?
Yeah, exactly. Filter ZTF data, and then they try to guess what kind of object they're looking at based off of some of that light group data.
Yeah. We've mostly used Antares, so I wasn't familiar with ALERCE.
Just for the guess at a classification.
I bet that's an acronym of some sort.
Yeah, the E is lowercase. So I don't know what you could come up with for that.
I was trying to remember which E was lowercase.
We are on number 5 right now.
Sorry, that's the Chilean broker.
Hmm.
Automatic learning for the rapid classification of events.
I see. Wow. I wonder what the Spanish word for alert is. Curious now.
Tack an A onto the end.
Ah, it's alerta. It's
Yeah.
not.
Just tack an A onto the end and call it a day.
Rafael, well said.
Okay, I've changed our exposure time. I don't know where my guess came from before, but it was not good enough. So we'll be here for 50 minutes total, 10 minutes have passed. So let's say 40 minutes, 40.
Perhaps I should take a moment to do my best attempt to explain what a broker is, what a transient broker is. I'll give it a shot, but please, there are many of you who know way more about this than I do. The way these transient surveys or surveys for variable objects work is as was described earlier. I think Kevin described it. You take a series of images through the same filter, and you look for changes. You look for things that move, things that brighten, things that disappear, things that appear, brighten or get fainter. And but you can imagine that this process is not perfect. You get a lot of spurious things, and just by looking at something's pattern of change or appearance or disappearance, you can get some idea about whether it's an instrumental artifact, something astrophysical, what kind of astrophysical object. So these brokers, they take in a stream of data, huge volume of data, so huge that it's not feasible for a single human brain or even a collection of human brains to do a meaningful job of searching for things that change, things that move. So this is all automated, and these brokers are designed to look at data from so-called time domain surveys, where you're observing things and looking for things that change in time. And it sort of takes that as input, and what it puts out, what the broker puts out, are sort of classified lists of this object could be a pulsating star, this one might be an exploding star, this one is probably spurious. So it's sort of a classifier slash, they're called brokers. They are event brokers or the alert brokers. How am I doing? Abhi, you're staying silent and really putting me on the spot.
No, I'm not putting you on the spot, but I can help out a little bit if you'd like.
Please.
I mean, so ZTF is actually the test case. The bigger thing is when Rubin starts the Large Synoptic Survey, every night from their large coverage of the sky and the number of exposures they'll have, we expect that they will see in a night as many as 10 million things that changed from a reference image before. This is completely impossible. Most of those things that change, a lot of them may be repeat things like variable stars, which you're not interested in if you have to follow up immediately. So the thing is, out of this large number of things, how do you find the ones that you need to follow up quickly. And identifying that and getting as much information, and as Raja says, trying to characterize or classify them to the degree it's possible, so that people can say, oh, I'm running this project, this object is interesting to me, I'm going to take it to the telescope. So it's to help sort through and winnow through that impossibly large number of events to find the ones that are interesting, because our capacity to follow up is much, much smaller than the number of things we're going to generate every night.
Thank
Sorry,
you.
I
That
should
was
have put
that's really
myself on the
beautiful.
camera, but
How many gigapixels is the Rubin camera?
I think it's 3 gigapixels.
Okay.
So I think 10 million a night is probably an overestimate, but that's the capacity to which things are being built. I mean, I'm familiar with Antares
Yeah.
because I, was one of the people that started it. So we were building to that scale.
I see. What is the largest format camera in use right now? Is the DES camera the largest thing?
I think so.
How many pixels is that?
So that's, let's see. It has 60 chips that are 4,000 by 2,000.
So 8 meg chips
8 meg chips and
times
60 of
60,
them.
so 480.
It's a half a gigapixel.
Half a
roughly, yeah.
gigapixel, okay.
Yeah.
Because CFHD megacam is something like 0.3 gigapixel, 320, but it's 36 CCDs,
Yeah.
each one is 8.
Yeah, they're all, I mean, in the same class. I
They're in
think
the same class, yeah.
distinction The distinction between 360 and 500 is pretty small, actually.
Yeah, yeah.
Yeah.
Compared to 3 gigapixel, which is
Right.
about an order of magnitude bigger
Right.
in area. So in number of pixels, sorry, not in area, number of
pixels,
pixels.
yeah. But it also covers 10.5 square degrees as opposed to 3 square degrees for DECam.
I see. So it'll be finer sample pixels.
They are finer sample pixels.
So you expect better seeing at the Rubin site then.
That's the thinking, yes.
And that's the difference between Pachon and Tololo. Or is it mostly dome seeing?
I think the engineering behind Rubin has taken care to minimize the effects of dome seeing. The building has been oriented so that it faces the common direction of the wind and things like that optimally. And all of those things. I think that the seeing at Pachon is a little bit better if you look at it from the dim monitors and the things like that, which stand out in the open as opposed to being inside a dome. Then the seeing is better at Pachon by a little bit at least.
I see.
And the challenge really is to build the telescope and the structures to deteriorate that as minimally as possible.
Right, because those can cause additional turbulence, etc. Now, so the Pachon summit is also where Gemini-North is that right?
Gemini-North is in the sort of the middle of it. On one end there's SOAR.
Okay.
And the other end is where Rubin is being built. Yeah.
And Tololo is not far away from there. I know I've been up to Pachon a few times.
No, it's not actually. There's a fork in the road, and if you go up, I think 9 kilometers or 10 kilometers, you're at CTIO. If you go the other way, 14 kilometers, you're at Pachon.
Right. Okay. And these sites are in Chile, and Pachon and Tololo are north of those is a site called La Silla, where the European Southern Observatory is. And further north is Las Campanas, where the Magellan telescopes are. And then even further north are Alma, Paranal, VLT.
Yes.
Right?
Yeah, but that's quite a bit farther up, I think.
Yeah.
Near. I may be mistaken, but I think the distance from Tololopachon to La Silla Campanas is
It's quite short.
quite short.
Yeah, you can see
You can
the
actually
La
see.
Silla.
You can actually see
Yeah,
La
you can
Silla
see that.
from.
You can see La Silla from during the sunset from Tololo, and you can
Yes.
see from Las Campanas. You can see La Silla to the south.
Sunrise.
But these other domes are
Yeah,
because of the curvature of the Earth, you can't see them.
that's true.
Is Alma relatively close to the Paranal, or
I think
no?
that's my impression. Now I would have to look at a map to really be sure.
Yeah,
Now
I've
that
never
you've
been
asked
to
me and
Alma.
put me on the spot.
Yeah, no, I've never been to Alma myself, so I don't know.
Yeah.
What's the name of the location that Alma is at?
Um,
I'm totally blanking.
no, it's in the middle of
Transients?
the. It's yes, Transients. Yes, Transients is another site next to it. I think
I see.
where they have the mid-infrared facility.
Look this up. I'm going to do a little snooping on Google and see if I can.
Yeah.
It's called San Pedro de Atacama,
Mm.
and it's near Antofagasta.
It's near Antofagasta. That I did know.
And the name, according to Google, the name of the town is San Pedro de Atacama, like that. This is where it's the Atacama Large Millimeter Array. And it has a beautiful.
That's the Chajnan tour, right?
Yeah, that's the. And of course, Alma means soul in Spanish. That's a beautiful acronym.
Okay, our first readout from this potentially bogus target. It doesn't look so bogus to me. It is in a host galaxy, so that's something to keep in mind, but it looks like the light is extended in a way that makes me think this is real.
It is or isn't extended, especially?
Pardon?
Are you saying it is or isn't extended spatially,
I
the
thought,
spectrum?
based on the slice vertically in this image, it looked like it had a portion of it that is faint and slightly more extended. Let me see if I can zoom in to show what I'm meaning. Wrong way. I mean, kind of hard to see. Oh my gosh, navigating this thing is difficult.
It
Yeah,
looks
maybe not
bright.
so.
It looks bright, so
Yeah.
probably is a point source.
It's off center from the galaxy.
I think it was. Let me go back to the image here. Oh, am I looking at the wrong one? Yeah. Yeah, the galaxy, it's off center, and it's the galaxy it's a part of is very faint. So
I don't think we'll be getting such a spectrum if this object were completely spurious, unless the galaxy has a bright nucleus of some sort.
let's happily call it not bogus.
have silicon lines?
Where do you see silicon lines?
No, does it have?
Oh, I don't. Oh, okay. In emission, you mean?
No, I mean, if it's type 1A, it should have them in absorption.
I'm wondering, so we, when you take the horizontal cut, we are seeing some, yeah, those are skylines.
Is this the red spectrum? Yeah.
This is the red spectrum, and it has a lot of cosmic rays.
Yeah, from such a long exposure.
What is the wavelength of the stitch? Is that at 5,500?
Yeah,
So that very bright night
57,
skyline could be
sorry.
5577. Sorry,
57.
Kevin, what was that?
5,700 is the dichroic.
Oh, so okay, 5,700. Okay, but we'd probably see 5577 on both sides because the dichroic is infinitely sharp.
Right.
So I'm thinking that's that line we're seeing. 5577 is one of
This
those
one?
two lines. Must
Yeah.
be. I think, yeah.
So this faint one here.
Yeah.
Anyway, I'm going to step out for a sec to make a fresh pot of coffee. Gotta make it through the rest of the night.
Well, this is fun.
Thanks.
I'm glad you invited
I'm
me.
making something similar later.
Thank you for coming.
Yeah, not at all. Yeah. I'll come to another one at the end of the month.
Please do. Thank you.
So I might sign off now. Thank you very much.
Thank you, Avi. Thank you.
Thank you.
We're a small enough group now that if people wanted to unmute and ask a question, please feel free to do that. And there's also the chat, of course, but so we haven't observed any Andromeda targets yet, right? Andromeda is still rising. Rafael,
Yeah, I
you were
believe
saying
so. I didn't put Andromeda up on like a finder chart like Kevin did, but I had to look for a bunch of transients to make some time.
no, this is given that it's early August. Andromeda usually isn't up till the second half of the night.
Yeah.
It's really so. And many of you on this call know this already, but Andromeda is a large galaxy, neighbor of the Milky Way, and it's a typical star in Andromeda. I mean, Andromeda as a galaxy is about 2.5 million light years away. So the light we are seeing now from Andromeda, not these objects, these are not in Andromeda, but when we observe Andromeda luminous variables and transients, the light we'll be seeing has been traveling for 2.5 million years. So old light from old events, old pulsations that we're analyzing now. It's old, we're analyzing them now, makes us sound like we're a lazy group of researchers. No, this is the finite speed of light means that's the best we can do. All we can do is look into the past. We can't really see the present and certainly not the future.
Do you know how the observing now are, or that we've been observing tonight?
Was your question how far away this particular transient is that we're observing tonight? We probably know that from the redshift of the galaxy. That is the host galaxy. But otherwise, since it's a transient and it's the first time it's bright and we're getting its spectrum, I don't think it was previously known. Our spectrum will probably tell us how far away it is after we've removed the atmospheric signature and all that. But it could well be that its host galaxy already has a known redshift and therefore a distance. But I don't know how far away it is.
And Andromeda is relatively close as galaxies go. How far away have we seen transients?
I think I can answer that. We've certainly seen transients like type 1a supernovae, they're really bright transients, easily halfway back to the Big Bang. So easily, the Big Bang happened 13.7 or let's say 14 billion years ago. So looking back 7-10 billion years, I think the most distant type 1a supernovae that discovered have been beyond the redshift of 1. I don't know off the top of my head what the most distant transient is that's been seen.
That's close enough. That's pretty far. Have transients turned out to be things other than supernova that we figured out?
They sometimes turn out to be novae in Andromeda. So these are mini explosions that don't destroy the star, but typically a white dwarf in a binary system that, onto which material is being dumped by the companion. Those are called novae. Similar phenomenon to a type 1a supernova, but the amount of material being dumped and the amount of material in the nuclear explosion is not, the energy is not great enough to completely disrupt the star. So the white dwarf remains, it undergoes an outburst, it's seen as a nova, then goes into a quiet phase again, and then repeats when some more material is dumped from the neighbor. So that's my understanding of how novae work. I may be mischaracterizing them.
So I assume a white dwarf in Andromeda we can't see except when it's doing this behavior.
Exactly. In its quiet state, we certainly, a white dwarf star at Andromeda's distances would be pretty much impossible. Not pretty much, completely impossible, even for Webb, and certainly it was for Hubble. So the faintest stars we could see and make good measurements of in Andromeda with Hubble are somewhat fainter than the sun. And a white dwarf is, if I remember correctly, it's something like, 1,000 times fainter than the sun. I shouldn't say fainter, less luminous than the sun, intrinsically less powerful. So if you put it, if you can barely see sun-like stars in Andromeda, something that's 1,000 times fainter is impossible to see with current technology. We know they exist. We see them throughout, the neighborhood of the sun in our galaxy, but we can't even see them throughout our own galaxy because the outskirts of our own galaxy are so far away that white dwarfs are undetectable. Stephanie, how are you holding up?
I'm just organizing the observation list right now and like adding the transients that we already did.
Got you. Do we have a target list that'll fill the night in case it stays clear throughout?
Yeah, I have 4 blue stars, 2 red supergiants, and 4 unclassified stars.
I see. All in Andromeda?
Yeah.
We're spending what of order 20 minutes, half an hour on each?
Yeah, it ranges from like 600 to 2400, but they're mostly like 600, 900.
I see.
2 are like 3000, but I think we should do like brighter ones first and then leave like fainter ones
For later.
We'll see when we get there.
And those are exposure times in seconds, right? 3000 would be almost an hour, 50 minutes.
Yeah.
Did the checkout go well? You're now a certified observer?
Yeah, he added me to the list of observers.
That's wonderful. It's a rare privilege because very few undergraduates get this, because it's through your hard work and having gained so much observing experience that you were given this opportunity. So well done.
Thank you.
Okay, back again.
What's this a finder chart for? The transients?
The next target, just because it is its host galaxy is more bright, and I just want to have the offsets if they're necessary.
Got you.
Yeah, it's not at the center of its host galaxy, and its host galaxy is pretty bright.
And the transient is what the red arrows are pointing to?
Yep. Just want to make sure I only pick stars as my offsets. Okay, that is a star. Come on. Yeah, that fuzzy blob in the center is the host galaxy.
Kevin, I don't think I saw the fuzzy blob at the center.
I can pull it back.
Okay, no problem.
Also, I don't know if the the resolution of the screen sharing goes that good. Come on. You see this fuzzy blob?
Yeah.
There we go. That's the host galaxy.
And where's the transient? Where the arrows are pointing?
Yeah, the intersection of the arrows. So it's slightly...
I see. So you're saying it's a little above the...
Yeah.
But this picture that we're seeing is taken before the transient.
Yes.
Not a during transient
right.
image.
I don't remember where it's downloading them from, but yes.
Got it.
Thought I said where it downloads them from on the code, but no, that's fine. Okay. And Sean, should I just send this to MH Techs? A finder chart.
I do not see an email yet.
No, I haven't sent it yet. I'm asking, should I send it to MH Techs?
And what is it you're sending?
A finder chart.
Yes, that's
okay.
Let's send it.
Okay. I'll just start a thread. But Emily and I were able to come to a consensus on the IMF mass weighting schemes.
Okay, I see the chart. Did it right.
That's wonderful. I was just talking to Connie earlier today in the office, but not about mass weighting. We just ran into each other.
Good.
So is the weight really that low for the
yes.
for the upper branch?
Yes. About a factor of 20 less than the lower branch.
I see.
But that's when you haven't taken into account the density profile. After you do the density profile, it's more like a factor of 80 to 20.
I see.
Anyway, so yeah, that was good. Emily's come around to my explanations, but she's right that there are still some weirdnesses in terms of the measurements that we get out at the end, like we're finding net rotation in all of the fields. So we're both trying to figure out what could explain that. Some of it might have to do with how we're using the KDEs. Some of it might have to do with the Tom Brown's isochrones don't go very low mass, and so they kind of truncate pretty early, and so you don't get a lot of nearby distances, or a lot of main sequence branch from those isochrones, and so that's part of it. So just playing around with that, and then finally the other thing that I'm you can see on my screen here I'm playing around with is I've just been using a single number to de-redden my HST photometry. I don't think that's the right way to do it, unfortunately.
What do you mean by not by a single number?
So if you have an extinction, like an EB minus V,
Mhm.
what extinct how do you correct that in the data? How do you remove that?
Right. So it depends on your filter. So right, if you're
Yes.
doing 606 minus 814, the color difference there won't be the same as EB minus V.
Correct. But regardless of that, it's not a constant value.
Across Andromeda, you mean?
No, not for Andromeda.
This is for Halo 7D.
Yeah, even for a constant EB minus V, it's not constant in color or in magnitude. This is, so for example, this is for a range of isochrones that I've reddened using like proper reddening techniques. What is the offset as a function of observed color? So like as the reddened color. And anyway, it's more complicated than just assuming it. The y-axis is the change in 606 from the unreddened isochrone. Anyway,
So it's like
this
an
is something I get to
extinction
play around with.
term.
Yes. Exactly. It's think of it as like a de-extinction term.
Not de-extinction, just extinction, right? Because it's the original magnitude.
I guess.
Original magnitude minus the observed.
Right.
So one thing I'm curious about, I still don't understand. So these, so I see the offsets. Are these different amounts of EB minus V?
They are, yeah. So it's not colored great. Here's a better version for a single isochrone. So one age, one iron. And I wanted to check what it looks like as you change age and iron. So that's what the other one is. But this is what EB minus V, or like for different EB minus Vs.
I see. So it changes the Y and it changes the X.
Yep.
Right. And so for these stars, of course, the EB minus V in Halo 7D comes from dust that's in the foreground of the stars. That's been pretty well mapped by various surveys.
Right. So I can measure the EB minus V easily, but to de-redden the observation is difficult. So the correct thing to do would be like what H3 does, which is to, while you're fitting everything, keep your data as reddened data, but also fit for reddening while you're measuring the stellar parameters, right?
But what I guess I'm. Let me see if I can. EB minus V is the change in the B minus V color caused by dust. For a given, if you adopt a certain reddening law, it's called,
right,
which is
the RV value,
which is RV is often used to characterize it, AV over EB minus V.
Right.
Assuming a given reddening law, a unique EB minus V, which every star should have, actually all stars in a given Halo 7D field should have.
Right.
Given EB minus V will correspond to a unique E606 minus 814.
Right.
Isn't that the only color we're using? Are we using other color baselines?
We're only using 606 and 814.
So then it should give you a unique value of the amount of reddening associated with, the amount by which to change the 606 minus 814.
Yeah, I haven't. I guess I could plot that. I haven't plotted that for the color change. I'm just showing the change in each one of the magnitudes.
Right, I see what you're saying, but they have to be shifted in both. But I think if you plotted, how are you generating these?
Comes from the same thing as the rest of my MIST interpolation scheme. Which is the same thing as what the MIST website is doing.
I guess what I meant was, if you assume a certain B minus V, how do you translate that to a 606 and other colors?
I start with RV 3.1, the classic, and then I define a bunch of EB minus Vs, and then AV is RV times EB minus V. So I have AV, right? I have reddening in the V band, or I have
How do you
extinction in the
get-
V band.
And
Sorry.
how do you get the A in the other filters?
I use the I don't know what you call them, photometry tables that MIST gives, which gives for a given, what do you have to pass it? You pass it. It's basically just a lookup table
Right.
that I'm
That's the dust.
interpolating
It
between.
must be the reddening law.
Yeah, it must be. But you have to give it you give it a TEF, a log G, a log luminosity, and an AV, and then it interpolates the nearest value to give you the reddened photometry.
The first set of parameters, all except AB, is just stellar parameters, right? And then you then give it an AB.
Right.
Okay.
That's what gives me my new photometry. So in this example here, you can see the original isochrone and then reddened. But each one of these points is not moving by, they're not moving by a constant value in color or magnitude.
I didn't understand that. Well, what do you mean by not moving by a constant value in color? Each of those curves should map onto, I mean, if you could shift the curve to the left and up, each of the reddened curves should match exactly with the original curve.
I mean, I guess it does. It's not, I guess that's true for a single isochrone. But when you're ignorant of which isochrone it came from, which is the kind of the question that we're dealing with here, right? Because I have just the raw photometry. What amount do you correct it by? And in the past, I just assumed one number because everyone, there's a number that people put online.
Well, I think we should use the one number that has been measured for each field, right? I mean, EB
no,
minus V
I have the EB minus V for each star. Yes, but how do you? I guess what coefficient do you multiply that EB minus V by to shift it back in terms of both magnitude and color?
That depends. So how do you shift it to how does EB minus V? What is the mapping from EB minus V to change in 606 and change in 814?
Yes, that's exactly what these curves are.
That should be a fixed thing. In other words, there's a fixed ratio for a given reddening law. Meaning, change in delta 606 divided by EB minus V is a constant independent of EB minus V. And the same thing for change in 814 divided by EB minus V. Those are constants.
That's exactly what I'm plotting here. It's delta 606 divided by EB minus V. The label is incorrect, but you can see in the code up here, it's divided by EB minus V.
Where is it divided? You're looking for
That's
that
okay. We can talk about. I gotta spend. This is what we're gonna talk about in tomorrow's meeting.
Got it. Okay.
Yeah.
All right.
I'll keep playing around with this to make sure that it's all good.
No problem.
But
No problem.
yeah, these are different isochrones, so different irons and ages and different extinctions. All plotted on the same figure. Anyway. Okay, where are we at in the night? I've got a couple more hours till Andromeda rises.
I see. I'm going to stop this STS session in a few minutes.
Okay.
Stop the recording, and we can stay on this Zoom call, of course, all night. It doesn't.
Right.
I'll reconnect in a bit. I might hop off for a bit and then reconnect.
Okay, we're reading out on red. I am sending new coordinates to POCO, and we are ready to move.
On the move.
And I'll get you a PA in just a second here. Right, so this is the one that I sent you a finder chart for. It is fairly faint at 19th magnitude, and it is not at the center of its host galaxy. So that's why I gave you the offsets, just in case that's helpful.
Okay. See what it looks like when we get there.
Sounds good.
Let me know when you have that PA.
Will do. I have a PA of 159.
159. Got it. Like that is your object. The red square.
Yeah, that's definitely the host galaxy. Yeah.
Okay.
Can you see like a bright source?
Increase exposure. Pull out.
Because if not, then it might be best to just go from offsets.
Right. Oh, definitely great spot. Going to 9 seconds.
Yeah. Let's just go from offsets. I'll sleep better at night or in the morning.
Do that up on the slip. We'll do a reverse offset.
Sounds good.
Oh. So if we can go to the blue offset at 34.2 east. .3 south.
Nice.
Okay, They're centered, going back to your target.
Perfect.
And take the slip back. You're guiding you maybe again.
Slit is opening. Slit has opened. And we are exposing. Okay, we'll be here for another 50 minutes.
Sounds good. You step outside and sniff the air.
Okay.
See if I can find anything with regards to that fire. in the morning.
I'm hoping you can't.
Good night, Denise. Thanks for coming.
Related to research, was anyone able to smell the corpse flower in Santa Cruz?
Yes, yesterday I went up to campus and
Did you get
got
to see
a
it? Did it
awful
just
whiff.
didn't it bloom 24 hours ago?
Yeah,
Yeah.
yeah.
Yeah,
Did you
it was
both
very
see
cool
it?
to see.
Yeah. I drove on like Saturday, I think, to try and see it. Or no, drove Friday night because we were told like that's when the plant was sending out the signals that it was going to be blooming. Then we got there and they're like, yeah, it's too cold in Santa Cruz for this flower to be outside.
Yeah.
And they thought it was going to be dead because it seemed to be sending the signals that it was no longer going to be blooming, but miraculously bloomed 24 hours ago, like overnight. And yeah, glad you get to see and smell it, Kevin. It's interesting, like it's not like puke-worthy smell by any means, but maybe like that first hour is really pungent.
Yeah, if
It's definitely
anything,
nasty.
yeah, if anything, it mostly smelled like a combination of like rotting fish and the worst bad breath you've ever smelled.
Yeah, no, like so as a snake owner, I know what a bad rat smells like, what like a little too decayed of flesh smells like, and it's like, yeah, it smells like rotting flesh.
Yikes.
Yeah, but it's not like the gnarliest rotting flesh I've smelled. Which is a funny, like something that I didn't think I'd be just using as a descriptor.
Yeah.
But
Well, we pull on our different experiences. Mine is growing up in BC, every